History of ocean acidification. During the Industrial Revolution, humans began burning fossil fuels to power machines and factories. This process releases carbon dioxide gas in the atmosphere in large quantities. This may not seem like a lot, but because the pH scale is logarithmic, this translates to 25% increase in acidity. The ocean is actually basic. It has a pH of 8.1, as opposed to the pH of freshwater, which is 7. So when we talk about ocean acidification, it does not mean that the ocean is turning to acid, but instead becoming less basic. This is an important distinction to make in order to understand the actual chemistry behind this phenomenon.
The effects of ocean acidification on sea life. The pH of the ocean changes within limits as a result of natural processes, and ocean organisms are well adapted to survive the changes that they normally experience. Some marine species may be able to adapt to more extreme changes, but many will suffer, and there will most likely be extinctions. We can't know this for sure, but during the last great acidification event, 55 million years ago, there were more mass extinctions in some species, including deep sea invertebrates. A more acidic ocean will not destroy all marine life in the sea, but the rise in seawater acidity of 30% that we have already been seeing is already affecting some ocean organisms. Acidification may also impact corals before they even begin constructing their homes. Larvae in acidic water had more trouble finding a good place to settle, preventing them from reaching adulthood. The eggs and larvae of only a few coral species have been studied, and more acidic water didn't hurt their development while they were still in the plankton. However, some of the major impacts on these organisms go beyond adult shell building. Mussels' byssal threads, with which they famously cling to rocks in the pounding surf, can't hold on as well in acidic water. Meanwhile, oyster larvae fail to even begin growing their shells. In their first 48 hours of life, oyster larvae undergo a massive growth spurt, building their shells quickly so they can start feeding. But the more acidic seawater eats away at their shells before they can form. This has already caused massive oyster die-offs in the U.S. Pacific Northwest.
Ocean acidification will have drastic effects on shelled organisms and on coral reefs. But what about its effects on humans? Many people mistakenly believe that the oceans may be turning to acid and that it will no longer be safe for humans to enter the water. This is not true, even in the most extreme scenarios for the next century. An ocean pH of 7.8 is not directly harmful to humans. In fact, many swimming pool maintenance guides suggest that people keep their pool pH between 7.2 and 7.8. So why would ocean acidification be detrimental to human health? The previous two lessons were focused on the marine food chain and on the coral reef ecosystem. Humans are closely linked to the health of the ocean. We have always relied on the ocean's resources for food, recreation, transportation, and medicines. From an interpretive standpoint, the important thing is to help people realize how they are personally connected to the ocean, and then to be able to explain to them how that connection is being jeopardized by ocean acidification. One of the most obvious connections people have with the ocean is seafood. Most of the shellfish we eat are going to be negatively impacted by ocean acidification due to the fact that they will be unable to build sturdy shells. Some oyster hatcheries in the Pacific Northwest have already been impacted and have seen declines in larval settlement and survival rates. Pteropods may seem insignificant to many people, but since they are a major food source for fish, their survival is very important to us.
One solution is literally to suck CO2 out of the water. There have been proposals to suck up the ocean's excess acid by throwing iron, limestone, or overline into the water, boosting plankton growth, adding to the building blocks for shells, or chemically absorbing CO2. But the energy needed to mine and distribute rocks and the unpredictable shift in food webs have made these ideas useless. Scientists have also been exploring the idea of seagrasses, kelps, and shell beds could counteract the rising tide of ocean's acidity in hotspots. Seagrasses, for example, could help coral thrive. Corals need aragonite in order to grow. However, acids in the water decrease the aragonite saturation value, and if it gets below 1, corals and shells start to dissolve. Today, most reefs have an aragonite saturation value of 3.8. Researchers found that seagrass meadows have the potential to increase aragonite saturation by up to 2.9 units, and the pH level by 0.38. This should give corals about an 18% boost in growth, making seagrass a potential solution to ocean acidification.
Seagrass may be a way to mitigate the problem, but to truly solve ocean acidification, we have to fix the source of the problem, CO2 emissions. Although there is evidence that the pH level of the ocean has cycled over time, the current drastic rise in ocean acidity seems to be directly due to human activities. This means it is up to humans to fix it, or we will ultimately cripple ourselves. Some solutions include reducing fossil fuel emissions or using alternative energy sources in an attempt to reduce the carbon dioxide concentration in the atmosphere. But it may be hard to reverse the exponential increase of acidity in the ocean, and since ocean plants produce 70% of the world's oxygen supply, it is definitely something to worry about.